So today we are going to talk about significant figures. Significant figures. So let's first of all write the definition, which is the significant figures. The significant figures are those reliable reliable digits and the measurement and the measurement of a physical quantity plus one additional additional digit plus one additional digit that is uncertain. That is uncertain. Also, let's write another point, which is the meaningful. The meaningful. So this meaningful. The meaningful digits. The meaningful digits in a number are called significant figures. So that's a much more simpler definition if you needed one. And finally, the last point that we're going to talk about is the number of significant figures in a measurement depends upon. So let's write this in another page so that it will be much more easier to see. So let me copy this and move it to another slide. Let's move it up here. Depends upon the precision limit of the instrument. So let's discuss the points. So the first point that we have, which is the definition, is the significant figures are those reliable digits in the measurements of a physical quantity plus one additional digit that is uncertain, which means when we are talking about significant figures, among all the terms, the last digit is uncertain. So what does it mean by uncertain? Let's talk about that. Suppose we have a scale. Generally, scales that you will find in the stationery will be about 15 centimeter. So I'm going to assume that is 15 centimeter. Plus, I'm going to make it so that the scale is not completely on screen, which means that the scale is much farther than it looks. So this commonly, let's suppose the scale is 15 centimeter. It is 15 centimeter. If it's 15 centimeter, then it will go from here to here. And since it is going farther, we don't know it's exactly 15 centimeter, but since it will be much harder for me to demonstrate that, so I'm using it like this. So now let's make some markings. So if you look at your scale, you will probably see markings like this. A bigger marking, which I'll make right now, might take some time, so you might skip the video for a bit. So let's make them as we can. So you will see markings like this in a scale. And if your scale is, the scale will actually have more marking than this if you are using the scale that I would expect normal students to have. So you will see sometimes there will be letters written upon this, generally 1 or sometimes 1 centimeter, since this is actually about 1 centimeter. 2, nothing is exact, but it's 1 centimeter, let's say it like that. 4, 5, 6, 7, 8, 9, 10, 11, and so on till 15 centimeters. And also and this line will be considered as 0. So this line will be considered as 0. But if you look at the scale that you have, if you see this part or any part in general, you will see that there are more divisions. So let's make this another color. Now if you look at this part, so I'm gonna make the part bigger to make it much more easier for us. So let's go back here, right here. So if you want to see this, I'm gonna take the 10 from here, so copy them and let's group them to make them smaller now. Okay, let's make them smaller. Let's copy one from there and let's move it right over here. So if you look at a scale, it will probably look like this. So let me count it if I'm right or not. So 1 2 3 4 5 6 7 8 9 10. So this should be right over here. Let's move them exactly together and let's move this one right over there. I think that's good enough. So let's write the markings. So this is 1, this is 0. So as you can see, this is 0 centimeter, 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, 5 centimeter, and so on. And among two of them, you will see like this. Sometimes the fifth one will also be greater. So if you see, this is 0, this is 1 millimeter. So this is 1 millimeter, 1 millimeter. This will be 2 millimeter, 3 millimeter, 4 millimeter, 5 millimeter, 6 millimeter, 7 millimeter, 8 millimeter, 9 millimeter, 10 millimeter, where 10 millimeter is just as is the same as saying 1, since 1 centimeter is equals to 10 millimeter. So as you can see, there are divisions right over here. There are 10 divisions. So, and this one is from here, the distance will be 1 millimeter. So instead of making them like this, you should actually make them like a distance. So the small distance. So if you have a, let's suppose you have a scale, probably you don't have much more accuracy than 1 millimeter if you think about it. Unless it's a special kind of scale, then generally it will just be 1 millimeter. So now let's talk about the scale. Let's go back to the scale and talk about it. So if you look at the scale, even if I wanted to measure something that is less than a millimeter, I can't. That means the minimum distance my scale can measure accurately is 1 millimeter, which means the least count or LC of my scale is 1 millimeter or 0.1 centimeter. So we have the least count when we're talking about the scale. So now I'm going to copy the scale so that I don't have to make him again. So let's group the scale, then copy it. Now let's move on to the next slide. So again, let's look at the definition to make it clear what we're trying to discuss. The significant figures are those reliable digits in the measurement of a physical quantity plus one additional digit that is uncertain. So now, suppose we took the scale, which is again consists of this, and let's also add the part that is like this. So let's copy them, let's move it right over here, then let's match it. I'm trying to make the scale as you would see in real life so that you get a glimpse of what I'm trying to show you. So let's move him a little bit. So when I try to move him a little bit, it's not working that well, so it might take some time. So when we're talking about least count, the thing that I was talking about, the least count means the minimum distance or the minimum something that I can measure reliably. So let's copy all of them. It's not exactly how it's supposed to be. Let's zoom it to make it much more clear. And generally the fifth one from the middle is generally raised, but this time I'm not the most accurate drawer, so it's not gonna be raised right now. But generally the fifth one, so this 1 2 3 4 5, this fifth one, so if I can, this fifth one is also actually quite raised like this. It's not as much raised as the previous ones, but so still 1 2 3 4 5, it is still raised. So now let's copy these two, then we can make them faster. So let's move on to the original size. Let's go boom, boom. I think that works. Then let's take all of them. If the scale is not in scale, don't mind it, okay? So we're just trying to demonstrate significant figures. We are not actually trying to create a perfect replica of scale. So let's look at the scale. So this is the scale. Suppose it was 15 centimeter. It does not matter since we don't care about that. Suppose now let's take a rod, okay? We are taking a rod. Rod are generally which colored? I don't know. I think they are gray colored, pretty silvery gray, so metallic gray. So let's take this. Suppose we have a rod, okay, and I keep it right over there. So we are measuring it with a scale. So let's zoom in into it to see where we are at. So first of all, let's do some markings so that it becomes easier. This is 0, this is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now let's zoom into it so that we can see what I was talking about. So if you zoom into it, you would see that the rod is greater than 6 centimeter, but by how much? So let's make a dotted line to see by how much. So let's make a dotted line. So this will be the dotted line, and probably making it of another color will be much better. Let's make it of blue, and also dotted line. I don't like blue. Let's make it something that pops. Red. I don't know how well does red pops, but it pops. Okay, so let's see here. If you look at the scale right over here, so this portion mostly, look at this portion, and let me change the color to be white. So if you look at this portion, you will see that the scale is 6 point something centimeters. So something centimeters. So it's probably between 6 this is 1 2 3 4 5 6 7, between 7 and 8 millimeters. So you can write 6.7 or 6.8 6.8 millimeters, sorry, centimeter. So if you think about it, I would say that is more towards 8. So you would think of writing 6.8, or you might think of writing 6.7. So we are looking close up, so it looks like that. But if you look at it from its normal scale, it looks like 6.8. So someone could write 6.7, someone could write 6.8. So as you can see, the two digits right over here, this 7 and 8, the last digits are uncertain. We are not certain about them. And also why we are not certain is, suppose the actual length, I'm just making this up, the actual length was actually 6.79123 centimeter, 1230000 centimeter. Then if you look at it, this portion right over here, this whole part was just instead of writing all of them, we just wrote the last digit. So we put all the blame into this one, 7 right over here. So you might write 7 or 8, depends on the person and how they see the scale. So now if you look at the scale, you have one uncertain digit, because it could be 7, it could be 8, but it could be 7.999. So you're blaming all of them here. But if you look at the 6, it is gonna be 6. So every term in front of it is actually gonna be a reliable digit plus one uncertain digit. So let's take examples of a few cases so that it becomes much more simpler for you to understand. Let's take another scale. Not that one, suppose this one. Let's take this scale, and let's take this scale so that it has a least count of, suppose this scale has a least count of 1 centimeter. Pretty bad scale if you ask me, since 1 centimeter, like, you can even, if you have a good sense in numbers, you can even pretty much guess how big is 1 centimeter. So let's think about 1 centimeter and let's look at some cases. Let's look at a case where it's almost exactly. So it's almost exactly aligned. Let's format it so that it's actually grayish color, metallic gray. So let's take two examples. One where it's exactly at 6, another one where it's more towards 6. After that, exactly between, not exactly like the by how much I exactly can, and finally of almost exactly 7. So if you look at these rods, let's talk about, so if I can move this, I would like to make another case which is more towards 7. So let's look at this. So our least count is 1 centimeter, which means the most accurate measurement we can do is from 1 centimeter. So this rod, you would say this rod is 6 centimeter, right? This is 6 centimeter, and I will make red the uncertain digits. So 6 will be our uncertain digit. Right over here, we have, so let's make arrows on everyone. Arrows, you get some arrows, he gets some arrows, and centimeter on the back. So in this case, since here, so let's take some other example. This will also be considered as 6. This will be considered as 6. This will be considered as 7. This will be considered as 7. So as you can see, all the terms in this case are uncertain, since even though you see it seems like it is exactly on 6, so talking about the first case, even though it seems exactly at it is at 6, since your scale can only measure till 1 centimeter, you're not sure. And if I zoom in quite a bit, it's actually not, it's even if it is exactly in 6, you can't say for sure, since you don't have a tool that can measure it much accurate than 1 centimeter. So that's why we would have to say that the 6 is uncertain, even though it looks like that. So in the second case, it's actually not even at 6. So 6 centimeter is not even true, since this portion right over here, I think, which color, let's do this color. So this portion right over here is outside, and it will probably be around 6.2 something something, which means 6 is uncertain. Also, let's look at this. This portion also, it will be uncertain. Similarly, here this portion, since if this portion was covered, it would be 7 centimeter. So some people write 7, but I think 6 will be much more appropriate, since the actual value will be 6 point something 9, something like that. And here in 7, it's not exactly 7, it's just close enough to 7. So our third one, our fourth one, and our fifth one. So we have some numbers, and we saw how why the last digit is called uncertain. Suppose we have a rod of 76 centimeter. Suppose we had a rod of 76 centimeter. So if we had a rod of 76 centimeter, then we would say 7 is certain, we are sure of 7. Let's say 976 centimeter. So 976, and finally the 6 will be uncertain, since it could be 6, it could be something else, if the least count is 1 centimeter. So this will be our conclusion. So that's the first point that we are talking about. So the last digit will be uncertain for any case. So even if it is exactly in line, you can't be sure that it is exactly in line, because you don't have a tool that measures it much more accurately. Think about it. If I had another tool, suppose I had a tool which least count of 0.1 centimeter, then it would say 6.0 centimeter. We would get the answer of 6.0 centimeter. Suppose we have, if this has a least count of 1 millimeter or 0.1 centimeter, we will get 6.0 centimeter. But you still can't be sure if it was 6.00 or 6.001. That's why you have to have an infinitely precise measurement, which will tell you if it's exactly 6 centimeter. So this is why you have to understand about significant figures, and why this last term is actually uncertain. So let's look at our second definition. Let's go back. So our second definition was the meaningful digits in a number are called significant figures. So let's look at this. Since our measurement was done in 6 centimeters, so let's go back over here, right here. So we have 6.8 or 6.7. So we have 6.7. Let's take it is 6.7. If it is 6.7, they are meaningful digits since you pretty much know it's gonna be 6.7 centimeters. The 7 might be a little off, it might be a little towards 8 or a little towards 6, but you know for sure that it's gonna be 6.7, right? And in this case, the uncertainty is actually plus minus 0.5. So we will talk about that quite a bit later. So let's also, the last point, which is also explainable by the thing that we did right now, the number of significant figures to measure depends on the precision limit. Precision limit in this case just means least count. So precision limit, so this part right over here just means least count for our case. So if a so this is just basically least count. So we're just talking about least count, and we talked about least counts with two examples, where a least count of 1 and where we had a least count of 0.1 centimeter. So just look at this. Suppose let's take our example 4 matches up. So if we had a least count of 1 centimeter, you would get that the rod is only 6 centimeter. You would think that the rod is only 6 centimeter and something else, but we don't know what that something else is. Whereas if you go right over here, you will see that it is 6.7 or 8. Still you're not quite sure it, because the actual value was actually 6.7912 something something. But you got closer since your least count decreased. So if you remember our previous lecture where we talked about accuracy and precision, you will remember the lower the least count, the greater the accuracy and precision. Sorry, the greater the precision. So that's why that's why least count and precision are very closely related. So now let's talk about another thing. Let's move on. Now another point that we're going to talk about, the precision limit. The precision limit of an instrument is the limit beyond which the instrument can't measure the physical quantity properly. So that's basically like least count. It's not the same as least count, but for your case it's almost basically least count. So just think of it as least count. Suppose we had a least count. Suppose let's take example. Suppose we had a least count of 0.1 centimeter, and here we have a least count of 1 centimeter. Suppose this, we measured a rod and this scale gave us 6 centimeter and this scale gave us 6.1 centimeter. By looking at this, which one would you say is more accurate? I would say this one is more precise. Sorry, not accurate, precise, since we talked about that accuracy and precision are not the same. So this one is more precise as well as accurate if the rod was actually near 6 centimeters. This one is more precise. And suppose this one confuses a lot of students. We said 6.0 centimeter and 6 centimeter. Which one is more precise? Some might think that 6.0 is basically 6. So they might say both are equivalent, which is wrong. It is actually this one. This is more precise. This is more precise. It's just that in this case that it was landed on 0. But sometimes it may land on 1, it may land on 0.2. It's just that it landed on 0.0 right now, which means this is more precise even though there is a 0. So now we talked about least count, we talked about precision limit, we talked about significant figures, and let's talk about how to count significant figures. I mean, we don't know how to count them off now, so let's learn how to count them. So rules to determine significant figures. So we have several rules and we will talk about them individually. So the first rule is all non-zero digits existing digits and zeros existing between the non-zero non-zero digits are significant. So if you're like me, you didn't understand what this is trying to say, but let's look at some examples and understand it. So I'm going to use another color so that it's much more easier to understand. Suppose we take a number which is 1 2 3 4. Suppose the number is 1 2 3 4. So what are the significant digits? So if you remember what significant digits are and look at the rule, which is all non-zero digits and zeros existing between non-zero digits are significant, this would have 4 significant figures, since 1 2 3 and 4 are significant figures. Also 4 is an uncertain figure, so let's make this another color, since 4 right over here is uncertain. So this has 4 significant figures. Let's take another example, which is let's keep it right over here, 1 2 0 3 4. So this right over here, look at the rule, there are 1 2 3 4 5, there are 5 significant figures. Let's take another example. Let's take 4 2 42 42.3. How many significant figures are there? It is 1 2 3. There are 3 significant figures right over here. The point does not matter, since the point could be placed anywhere and it would still be the same. So let's talk about something that this does not consider, which is zeros in front of non-zeros digits are not significant. Because think about it, writing 1 centimeter and writing 0.1 centimeter are the same. So this does not add any new information, whereas 1.0 centimeter adds a new information, which means this is more accurate than this. But in this case, this and this are same, whereas this is more accurate than the previous one. So this is something that you must know, and we will probably talk about it later. So now let's talk about the second rule, which is zeros at the beginning and end of a number are not significant. So let's take example, and I will ask you to find the number of significant digits in this case. So let's take our pen. Let's take example. Let's say 0001 2004 500. So look at the zeros in the beginning and the end, so ignore them. So we are going to ignore these zeros and these zeros. So let me take them to gray color. So now let's look at the terms. There are 1 2 3 4 5 6, so which means there are 6 significant figures. So from my previous explanation, you might understand why the zeros in front of them, the 3 zeros in front, would not be significant. But what about the 2 in the end? So I did not talk about that, so let's talk about that right now. So let's talk about why the 2 zeros in the back are not significant. Suppose let's have a ruler which has a least count of 1 meter. Okay, suppose it has a least count of 1 kilometer. Okay, and you got the value as you measured, and you got the values as 2 kilometer. Of course, you can write 2 kilometer as 2000 meters, but these zeros in the back are not significant. Do you know why now? Since the least count is only 1 kilometer, the zeros here, right over here, they just happen to come about because 1 kilometer is 1000 meters. It's not the fact that it measured that it is 2000 meters. It actually measured 2 kilometer, which means it could be it could be 2137 kilometer or something else. So it could be something else entirely, but we wrote 3 zeros to convert it. That's why the zeros in the back don't matter. So if you want to show that the zeros in the back matters, you would have to show them by a decimal point. For example, if I wrote 1.12.0 or 120.0, then this zero that I'm highlighting will be significant since you're keeping the zeros even though there is a decimal. So if the zeros, so if you want this 2 zeros to be significant, you would have to keep a decimal point right over there. Since if you keep a decimal point right over there, it means that everything that you measured was measured within the limits of the least count, which was actually measured, and these zeros are not placeholders. So when converting 2 kilometers to meters, you're just keeping the 3 zero for placeholders, but you don't exactly know if there are 3 zeros or it could be 137, since it can only measure 1 kilometer. So sorry, 2.137. Suppose this, let's change this to meter, sorry. So 271 or 2.137 kilometer, dot dot dot. So if you look at here, since the least count is 1 kilometer, it will never be able to measure this part, which means when converting, this will be the actual measurement. But if you look here, the 3 zeros are just placeholders when converting the units. So that's what I'm talking about when the zeros at the end and the beginning are not significant. So I hope you understand. If you didn't understand, what was this back, and try to clear it up for yourself. So another one, the third rule that we are going to talk about is the zeros which lie right to the decimal point, and left to a non-zero digit are not significant. So what's right and what's left? That might be a question for you. But for me, I think I know what's left and right. So left will be this direction and right will be this direction. I always think about I write with my right hand, so I look at my hand and I find out the direction. So it's a neat trick. I think I should actually like have it known in general, but it doesn't matter right now. So let's look at this. 0 to 0.0023. This has two significant figures, so you might be confused. So let's take example. 120 has two significant figures. 120 dot has three significant figures. 12.0 has three significant figures. But why does 2.00023 only have two significant figures? Since it's basically like this. Suppose you had let's take an example. Since we're using lens is the most easiest to understand. So suppose I measured 1 millimeter with my scale, and the scale has a least count of 1 millimeter, and I measured 7 millimeter. So if I convert it to centimeter, it will be 0.7 centimeter, and if I convert it to meter, it will be 0.007 meters. So think about it. Are the zeros significant right here? No. Why are they not significant? Because you're basically writing 0.7 meter. So it's basically like this, because the measured data is only 7, and these are just the numbers in front of it. So that's why this will not be significant. So think about it. Let's go back to our previous cases where I talked about. Let's try to find it. So like this one, 1 centimeter is the same as 0.1 centimeter. It's the same right over here, since the measured value is only 7, and you're adding zeros in front of it, which does not matter, and the point also does not matter. So that's the third rule. Now let's look at the fourth rule. So this might be a little bit confusing, so rewatch the video and get the idea of how to use them. I'm going purposely slow to make it much more clear and much more understandable. So the fourth one, the fourth rule, I mean there are a lot of rules, but once you understand all of them, it will be much more easier for you to understand them. So the fourth rule, the zero existing, the zeros existing to the right, to the right of any non non-zero digit after the decimal point, after the decimal point, after the decimal point, after the decimal are counted as significant figures, are counted as significant figures. So let's take example, and you have to say how many significant figures are there. Suppose I took an example which is 85.00. If you said there are two significant figures, you would be wrong. There are actually four significant figures. Because if the two trailing zeros, these are called trailing zeros, were not significant, you would have not mentioned them after the decimal point. So if you remember the previous, I think it was rule 2. So if you put a decimal point and you mention them, they are important, which means they are significant figures. So these two zeros were also measured by your instrument. It's just that in this case they were zeros, and in some other case it could have been 85.1 if it was 85.01, if it was something else. So let's take another example. So, and you tried 0.00580. So the first three zeros, so these zeros right over here, are not significant. Why? Because they are zeros that were just placed in front of it and which was not actually measured. And the zero in the end, which is written, which means it is important since it's coming after a decimal point. So you could have removed the zero and it would not be the same. So let's think about something, and let's go behind a little bit. Why does 700 only have one significant figure, whereas 7.00 has three significant figures? So look at here. If we don't write two zeros right over here, it will only be 7 instead of 700. So the value has gone. Which means the two zeros are just placeholders to say that it is on the 7 is on the hundreds place. Whereas in this case, if you didn't mention the zeros, it will still be 7. Even if you mentioned it or not, it will still be 7. That's why there are three significant figures, which means that these two zeros are trailing zeros are important. They were actually measured that they were zeros. So right over here, this will have three significant figures. Three significant figures. I hope that was pretty clear. So if you didn't have zeros right over here, it will lose the value. It will not be 700, it will be 7. But whereas if you lose the two zeros right over here, it will still be 7. So just adding the two zeros means that it tells us that the device is very accurate and the accuracy of the device. So the fifth rule that we are going to talk about, the fifth rule, the power of 10 are not significant, are not significant. So let's take an example, a simple one, then go back. Let's take an example, which is we had 700. So 700 can be written as 7 into 10 to the power squared. In this case, there is only one significant figure, and I hope you understand why there is only one significant figure, because we already talked about it right over here. But if I wrote this, but instead of 7 into 10 to the power 2, I wrote 7.0 into 10 to the power 2, there will be two significant figures. Since this 0, I could have not written the 0 and it would still be 7 into 10 to the power 2. Since I wrote the 0, it means that it was actually measured. And if I had 7.00 into 10 to the power square, it will be three significant figures. So let's take an example and you try it. So if I had an example, 24 times 10 to the power 6, how many significant figures are there? There are two significant figures. 2 and 4 are the significant figures. Even if I kept a point right over here, there will still be two significant figures. And if I get 0.024, it will still be two significant figures. So the power of tens does not change, because I can actually change the value of this pretty easily. So if I can write 2.4, then it will be 10 to the power 7. There will be still two significant figures. I can write 0.24 into 10 to the power 8, or I can write 0.024 into 10 to the power 8, and so on. Sorry, 10 to the power 9. And still, in all of this case, there will only be two significant figures, which are 2 and 4. Now, let's look at the third one. Sixth. The sixth rule that we're going to talk about is constant having infinite significant figures. Constants have infinite significant figures. So you might think, huh? Why? Because they are constants. But why? Because they are constants. Why? So if you're like that, I will explain it to you pretty easily. Suppose let's look at some examples. So the examples of this will be Avogadro's constant. Avogadro's constant, you will learn more about this in chemistry lectures, which I will make videos about. I don't think pretty quick, but I will make videos about them. So refractive index, pi. Okay, so we have this. These are also some examples. Suppose I said there was a constant. Okay, I'm just assuming. Suppose, let's say my constant is 3. This has infinite significant figures. Why? Because even though in general term or layman term I am saying C3, since it is known to its highest position, which is 3.000000000, it has infinite terms, and I know all the terms. So hence it has infinite significant figures. Even though it's 3.0000000, there are infinite significant terms. But let's look at pi. Pi, if you know about it, is 3.14 point something something something. I don't know all of them, but there are a never-ending amount of terms, and which are all important, which are actually all measurable, since it is a constant that is known to a high degree. Since pi is actually never ending, we are sure that it is never ending, and we are sure that every term is fixed and every term is unique, so there is no repetition, which means pi is actually has infinite significant figures. And let's look at some other significant figures. Let's look at Avogadro's constant. Avogadro's constant, it is approximately 6.023 into 10 to the power 23. So the value is approximately this. So if you look at this value, even this is not the exact value. Suppose this was the exact value. Suppose it was the exact value. This is not the exact value, but suppose it was the exact value. You would see that it only has 4 significant figures. So the significant figures are 4. But if you actually wrote them, if you write like this, they would think that the significant figures are 4. But you can actually write this as 6.02300000000 if it was 6.30223. It is actually a little bit longer, and I think it has more significant figures than 4. Of course, it has infinite, that we know. But what I'm trying to say is, suppose, let's not look at this. Let's think of something else. Suppose there is a constant 6.03. So even though you would write it like this, there are infinitely many trailing zeros, which would mean there are infinite significant figures. Even though you might think when you're writing in general terms, you would only write the first 4. But even though there are infinite significant figures, which means every number that you know, 1, 2, 3, 4, every number has infinite significant figures, because they are constants. Because 1 is a constant, 2 is a constant, 3 is a constant. What is not constant is the length of your rod, because the length of a rod can be, suppose the length of a rod is 6 point something something centimeter. If you measure it, it can be 6 centimeter. If you measure it more accurately, it can be 6.1 centimeter. If you measure it more accurately, it can be 6.12 centimeter. You can keep on going. Even though it looks like 6.12000, you don't know. After 1,000 zeros, there will be a 1, there will be a 2. So that's why constants have infinite significant figures, whereas other terms have to be known by their least counts. So I hope you understand right now. So now let's look at some notes to understand how you find significant figures when you're adding, multiplying, subtracting, dividing, blah, blah, adding, subtracting, multiplying, dividing. So let's look at some notes, and which will probably help you. I don't know. So in addition, so when you're adding, in addition or subtraction, since addition and subtractions are two parts of the same coin. So in addition and subtraction, the final result, which should retain as many decimal places as there are in the number with the smallest or least number of decimal places. So let's take a look at an example to understand much more easily. So if you take an example, if you added 2.42 plus 1.32 plus 0.2, so if you just press this in a calculator, you would actually get 3.94. So if you're doing calculations for math, this is correct, but if you're doing it for physics and when you're doing calculations, this is wrong. It's actually supposed to be 3.9. okay, so you might think why. This is the rule, and let's talk about why is it the rule. So look at here the least count is, so let's take another color. Here the least count is 0.01. Here the least count is also 0.01, whereas here the least count is 0.1. So if we had a better instrument that could measure this, it could actually be 0.29. You don't know, it can be 0.29. It's just not right now because we are using tool which has less measurement. It could be 0.20. We don't know. It's the range. Look at the range. It's an insane range if we had same significant figures. So just look at the range. So if it was 9, this value will be just like, it would change. That's why when adding or subtracting, you look at the thing which has the least significant figures and just say that that's the answer. Because if you add 4, you're not certain of the 4. Like, even when you're talking about the 9, you're not certain about the 9. Now you add 4, that's a very bad thing to do. So that's why when you're doing this, you're doing that. So because it could be 0.29, 0.20. If it was 0.20, it would be 3.94. But if it was 0.29, so let's do that. 2.42 plus 1.32 plus 0.29, the value you will get is actually 4.03. That's why when you're doing calculations like this, you will only see the last two digits. You will only keep the digits which has the least number of decimal places. Okay, so that's the rule with addition and subtraction. I hope that was understandable. Now let's look at the second, when we are multiplying or dividing. So in multiplication or division, so multiplication and division, there are also like subtraction and addition, but something else. So multiplication can be said as glorified addition, and multiplication and division are the same sides of the different sides of the same coin. I'm not sure of the proverb, but you get what I'm saying. So in multiplication and division, the final result should retain as many significant figures as are there in the original number, with smallest or least number least number of significant figures. So basically the same as that of addition or subtraction. We are basically doing the same thing, but in addition and subtraction it was pretty easy to explain, and in multiplication and division it will be quite hard to explain. To just think about it in the same way that we thought about in addition and subtraction. So that's why. So let's take example. Suppose we had to find the density, and we were given the mass and the volume. Suppose the mass that we were given is 4.237. So this has 4 significant figures, and the volume was given 2.51, which is 3 significant figures. The units of the mass were gram, and the units of volume were centimeter cubed. So if you actually do the calculation, if you use your calculator, you will get 1.68040780.876 gram per centimeter cube. But are all the terms important? Are all the terms significant? Is it actually something that you will find if you measure it with a more accurate measurement? No, because the volume is not too well, the volume and the mass are not such accurate that it will give that result if you measure it. Even if you measure it, you will get the accuracy of only the first 3 digits. So this will be only accurate when you use them. So this is actually nonsense because of the volume. The volume has 3 significant figures, so the result, which is the smallest or least number of significant figures, which means 1.68, or if you round it off, you will get 1.69. We will talk about rounding off numbers in the next video, but if you look at this, the later part of the 3 digits are not important at all, because that's not the exact value. The exact value is only 1.69. So the value we will get is 1.69 gram per centimeter cube. So why it was 9? It is because of rounding. We will talk about rounding off of the numbers in the next video. So let's actually conclude this. So here density is reported to 3 significant figures, since the smallest number of significant figures is 3. So in the next video we are going to talk about rounding off of numbers. Till then, bye bye.